The story begins over 2,000 years ago, around 400 BCE, with a Greek philosopher named Democritus. He suggested that everything in the universe is made of tiny particles that could not be cut any further. He called these particles atomos, meaning indivisible. Much later, in 1805, the English scientist John Dalton published the first scientific atomic theory. Dalton proposed that all matter is made of tiny particles called atoms, which he believed were solid, hard spheres. According to his theory, atoms could not be created or destroyed, and all atoms of the same element were identical. Towards the end of the 19th century, experiments suggested that atoms were not indivisible after all. In 1897, J. Thomson discovered a tiny negatively charged particle called the electron. This led to the plum pudding model of the atom, where electrons were embedded in a sphere of positive charge, like raisins in a Christmas pudding. In 1909, Ernest Rutherford tested this model using alpha particles and a thin sheet of gold foil. Most particles passed straight through, but some were deflected. This showed that atoms are mostly empty space, with a small, dense, positively charged nucleus at the center. Niels Bohr later adapted this nuclear model by suggesting that electrons orbit the nucleus in fixed energy levels, known as shells. His calculations matched experimental observations. Further experiments revealed that the positive charge in the nucleus is made up of smaller particles called protons. Then, in 1932, James Chadwick discovered the neutron, a particle with mass but no electrical charge. These discoveries led to the modern atomic model, which is still used today.
Atoms are incredibly small, and surprisingly, most of an atom is actually empty space. At the center of every atom is a tiny core called the nucleus. Surrounding the nucleus are electrons, which move around it in shells, also known as energy levels. The radius of an atom is about 0.1 nanometers, or 1 × 10 to the power of -10 meters. The nucleus is much smaller, about 1 × 10 to the power of -14 meters. This means the nucleus is less than 1/10,000th the size of the atom. Atoms are made of 3 types of subatomic particles: protons, neutrons, and electrons. Protons have a positive charge and are found in the nucleus. Neutrons have no charge and are also in the nucleus. Electrons have a negative charge and move around the nucleus in shells. Protons and electrons have equal but opposite charges. In a normal atom, the number of electrons is equal to the number of protons. This means the charges cancel out, so the atom has no overall electrical charge. Protons and neutrons have a relative mass of 1. Electrons have a very small relative mass, about 1/1840, so their mass is usually ignored. Because protons and neutrons are found in the nucleus, almost all of an atom's mass is concentrated there. Each type of atom belongs to an element, and every element has its own chemical symbol. Chemical symbols are 1- or 2-letter abbreviations. The first letter is always capitalized, and the second letter is lowercase, for example, C for carbon and Mg for magnesium. Some symbols come from English names, while others come from Latin. For example, sodium has the symbol Na. There are 118 known elements, all arranged in the periodic table.
The atomic number of an element is the number of protons in the nucleus of an atom. All atoms of the same element have the same number of protons, while atoms of different elements have different numbers of protons. Atoms also contain electrons. In a neutral atom, the number of electrons is equal to the number of protons. Because protons are positively charged and electrons are negatively charged, these charges cancel out. This means atoms have no overall electrical charge. For example, sodium has an atomic number of 11. This means every sodium atom has 11 protons and 11 electrons. Now let's look at mass numbers. The mass number is the total number of protons and neutrons in the nucleus of an atom. Atoms of different elements usually have different mass numbers, but sometimes they can be the same. For example, both argon and calcium can have atoms with a mass number of 40. We can use the atomic number and mass number to calculate the number of subatomic particles. The number of protons equals the atomic number. The number of electrons equals the atomic number. The number of neutrons equals the mass number minus the atomic number. Atoms of the same element must always have the same number of protons, but they can have different numbers of neutrons. These atoms are called isotopes. Isotopes have the same atomic number but different mass numbers. Isotopes are named using the element name and the mass number. For example, carbon-12 is an isotope of carbon with a mass number of 12. All isotopes of an element have the same chemical properties because chemical properties depend on the number of electrons. The relative atomic mass of an element is the average mass of its atoms, taking into account all of its isotopes and how common each isotope is. Relative atomic mass is shown in the periodic table and is represented by the symbol AR. It's important not to confuse mass number with relative atomic mass. Mass numbers are always whole numbers, but relative atomic masses are usually decimals. Let's look at an example. Chlorine. Chlorine has a relative atomic mass of 35.5. This is because chlorine exists as two isotopes, chlorine-35 and chlorine-37. Relative atomic mass is measured by comparing atoms to carbon-12. 1/12 of the mass of a carbon-12 atom is used as the standard. Now let's calculate the relative atomic mass of chlorine. Chlorine-35 has an abundance of 75% and chlorine-37 has an abundance of 25%. This means that out of 100 chlorine atoms, 75 have a mass number of 35 and 25 have a mass number of 37. To calculate relative atomic mass, we divide the total mass of all the atoms by the total number of atoms. All substances are made of atoms. An atom is the smallest part of an element that can exist. An element is a pure substance made of only one type of atom and cannot be broken down into simpler substances by chemical reactions. There are around 118 known elements, shown in the periodic table using chemical symbols. Most metals are found on the left and center of the table, while non-metals are found on the right. Some elements, such as helium, exist as single atoms. Other non-metal elements exist as molecules, which are two or more atoms chemically bonded together. These molecules may contain atoms of the same element, such as hydrogen, nitrogen, or oxygen. Even when they form molecules, these substances are still elements because they contain only one type of atom. For example, oxygen naturally exists as a molecule made of two oxygen atoms bonded together. When atoms from different elements are chemically bonded, they form a compound. A compound is a pure substance made from two or more different elements, chemically combined in fixed proportions. Compounds are represented using chemical formulas. For example, Water, with the formula H2O, contains 2 hydrogen atoms and 1 oxygen atom. Carbon dioxide, with the formula CO2, contains 1 carbon atom and 2 oxygen atoms. Unlike elements, compounds are not shown on the periodic table. A particle is a very small piece of matter and can be an atom, a molecule, or an ion. A mixture is a combination of substances that are not chemically bonded and can be mixed in any proportion. In a mixture, each substance keeps its own chemical properties. For example, air is a mixture of different molecules, including nitrogen, oxygen, water, and carbon dioxide, where all substances remain unchanged. Mixtures can be separated using physical methods, such as filtration, crystallization, simple distillation, fractional distillation, and chromatography. These processes do not involve chemical reactions, and no new substances are formed. In chemistry, a pure substance is something very specific. It contains only one element, like oxygen, or only one compound, like pure water. A mixture, on the other hand, contains 2 or more elements or compounds that are not chemically combined. In a mixture, each substance keeps its own properties. Nothing new is formed. Mixtures are not chemically joined. They can be separated using physical processes. These processes do not involve chemical reactions. They simply separate substances that are already there. But how we separate a mixture depends on what kind of mixture it is. Let's start with filtration. Imagine mixing sand and water. The sand does not dissolve, it just sits there. To separate them, we use filter paper. The paper has tiny pores. Water molecules can pass through easily, but the sand particles are too large, so they get trapped. This is how filtration separates an insoluble solid from a liquid. Next comes crystallization. Now imagine salt or copper sulfate dissolved in water. You can't see the solid anymore, it's fully dissolved. To get it back, we gently heat the solution. As the water evaporates, the solution becomes more concentrated. Eventually, solid particles begin to form again, arranging themselves into crystals. If this happens slowly, the particles have time to form neat, ordered patterns, creating larger, clearer crystals. This method is often used to make copper sulfate crystals in the lab. Now let's look at simple distillation. Think about seawater. It looks like one substance, but it's actually water mixed with salt. Salt has a much higher boiling point than water. When seawater is heated, only the water evaporates. The water vapor moves away, cools down, and condenses back into liquid water, now pure water. The salt stays behind in the flask. That's simple distillation, separating a solvent from a solution. But what if a mixture contains 2 liquids? That's where fractional distillation comes in. Imagine a mixture of ethanol and water. They both evaporate, but at different temperatures. As the mixture is heated, vapors rise up a tall column that is hot at the bottom and cooler at the top. Each liquid condenses at a different height depending on its boiling point. Liquids with lower boiling points, like ethanol, condense first and are collected at the top. Liquids with higher boiling points, like water, condense later. This same idea is used on a huge scale to separate crude oil into useful fuels. Finally, let's explore paper chromatography. Imagine you place a tiny dot of ink on a pencil line drawn across paper. When the paper is placed in a solvent, the solvent slowly travels up the paper, carrying the ink with it. But here's the trick. Different substances in the ink move at different speeds. Chromatography works because there are 2 phases, the stationary phase, the paper, the mobile phase, the solvent moving through the paper. Each substance is attracted differently to these 2 phases, so they separate as they move.
The result is a chromatogram. This chromatogram can tell us a lot. A pure substance produces one single spot. A mixture produces two or more spots. Chromatograms can also help identify substances. If two samples produce the same number of spots with the same colors and the spots travel the same distance, then the substances are likely to be the same.